Hi, my name is Olavo Silva from Federal University of Santa Catarina, Brazil, and I will talk about numerical modeling of low-frequency acoustically induced vibration in gas pipeline systems. In oil refinery plants, the structural vibration behavior of gas pipeline systems can be strongly affected by the response of the acoustic domain represented by the gas being transported through pressurized pipes, cylinders, and other related components. In the hydrotreating process, for example, hydrogen gas must be pressurized to high pressures. Large reciprocating compressors are used to reach this objective. The gas pulsation produced by this kind of machine is an important source of excitation for the pipeline system. So the structural behavior of pipeline systems can be strongly affected by the fluid flow through the pipes, which lead to flow-induced vibrations. In the book of Kaneko et al., we have a nice diagram to classify the types of mechanisms involved in flow-induced vibrations. Here, we are only interested in single-phase flow, not in two-phase flow, for which two types of flow may occur. Steady flow, as external flow, like wind loading, etc., and as internal flow, like in this picture. And unsteady flow, as pulsating flow, turbulent flow, and sudden change in flow, like the water hammer phenomena, for example. Considering gas, a pulsating flow can be related to suction and discharge of compressor systems, where the energy is concentrated at the first harmonics of the rotation frequency. In this case, in general, internal longitudinal acoustic modes are activated, causing the pulsation of the pipe wall, which leads to equivalent loads on elbows and so on. And the turbulent flow can be related to turbulences and vortex caused at discontinuities like valves, expansions, etc., depending on the velocity of the flow. In this case, internal higher order acoustic modes can be activated, causing higher order modes of the pipe wall. Both mechanisms can cause a failure of components in a pipe system, but in this project, our focus is on the acoustically induced vibration by pulsating flows, mainly at the excitation frequencies related to the first harmonics of compressors pulsation. So, the objective of this project is the development of a numerical procedure to model low-frequency acoustically induced vibration caused by compressor pulsation in gas pipeline systems, adaptation of the obtained procedure to an open-source software, the OpenPulse, and sharing OpenPulse with pipeline engineers while the development is in progress to help us to validate and improve it. The methodology is based on the following assumptions. The fluid is a gas. The excitation frequencies correspond to the first harmonics of the compressor's pulsation. In this case, friction between gas and pipes is negligible. Acoustic plane waves propagates in the axial direction, 1D acoustics. Each pipe is linearly elastic with length much larger than the diameter, and the deflections are small compared to the pipe thickness, enabling the use of beam structural models. And we are considering time harmonic problem. Besides that, we are considering a weak coupling between structural and acoustic fields, one-way coupling, where firstly we solve the acoustic problem with acoustic properties updated according to some structural properties, and considering 1D acoustics with the finite element transfer method, FETM. After this, we solve the structural problem considering the internal pressure field imported as element internal loads with fluid mass effect, and using 3D Timoshenko bin with the finite element method, FEM. So we have the final result. Now, first of all, let's talk about the modeling of the time harmonic acoustic problem. The transfer matrix method, TMM, is a popular technique to build discretized models for performing analytical and numerical studies on the plane wave acoustics in pipe systems. This method is particularly efficient to deal with plane acoustic waves in tubular circuits, where two scalar fields are sufficient to describe the waves, the acoustic pressure P and the acoustic volume velocity Q. Considering relatively low frequencies and the wave equation, one can find an acoustic transfer matrix T between the fields after and before a finite tube. However, this is based on a mixed formulation, which is not interesting to develop a finite element-like method. A few algebraic operations need to be done to rearrange the variables of the mixed formulation into one not mixed, the same type of variables in each nodal vector, which is more suitable with finite element matrices. This method is known as finite element transfer method. Here we have now the acoustic admittance matrix for a tube element, which relates the pressure field with the volume velocity field. Now, we can develop a numerical procedure based on finite element tubes with 2 nodes per element and 1 degree of freedom per node, the acoustic pressure. An FETM mesh can be built for which the assembled element matrices generate the global acoustic problem to be solved to find the global pressure field. The acoustic boundary conditions considered are nodal volume velocity and pressure, for considering the compressor load, for example, or other excitation, and nodal impedance to consider valves, terminations, reservoirs, etc. In our implementation, we also consider the capability of considering a mean flow velocity, the adjustment of effective element lengths depending on the transition of pipe diameters, for example, in expansion chambers and side branches. The material properties related to specific regions, making it possible to change gas properties according to the operational characteristics of each region of the domain, according to temperature, mean pressure, etc. In addition of dissipation through inserting a complex wave number, if needed. After the acoustic model, let's talk about the time harmonic structural problem. Here we are considering the Timoshenko 3D bin theory, which considers shear stress and 6 degrees of freedom, 3 translations, and 3 rotations. We are considering linear elastic materials. From continuum mechanics and applying the principle of virtual work, one can find a variational equation that relates strain, stresses, and vibrations. Through the Galerkin methods, the translations and rotations fields are discretized, resulting in the bin finite elements, with 2 nodes per element and 6 degrees of freedom per node. The element stiffness matrix is composed of 4 parts related to bending, shear, torsional, and axial stiffness. The mass element matrix is composed of 2 parts, the translational and rotation mass. And here, the element force vector. Now we can develop a numerical procedure based on the finite element method with mesh for which the assembled element matrices generated the global vibration problem, here considered with viscous and hysteretic damping. The boundary conditions considered are nodal forces to simulate some external loads, nodal displacement and rotation to consider the compressor vibration, for example, and we can add mass, springs, and dampers to simulate some types of supports. In our implementation, we also consider the possibility of applying an offset between local coordinates and the beam's neutral axis, the calculation of sections and shear correction factors through a finite element mesh of each section. Different materials can be associated to different regions, making it possible to change pipe properties according to operational characteristics of each part of the domain, and addition of distributed mass for representing insulation material, if relevant. After defined and implemented the acoustic and the structural models, it's time to explain the weak coupling between the two physical domains. The speed of sound in the gas is updated according to the mechanical properties of the wall, diameter, Young modulus, and thickness. And the effect of the internal pressure field obtained after solving the acoustic problem is considered in the structural model as an equivalent axial load resulting from the stresses field induced by the internal pressure and neglecting the radial inertia of the pipe wall for low frequencies. The stress field is composed of radial and hoop stresses obtained from the plane state analysis of each element section. If the element belongs to a capped end pipe, an axial stress must be considered. This equivalent load, axial load, is applied as an element load, element by element, with the corresponding superposition depending on the assembling processes. So, we can use the same mesh for both models, nodes, elements, and connectivity, solving the acoustic problem with the equivalent speed of sound and, after this, transferring the pressure field to the structural problem, which converts the internal pressure of each element in equivalent axial element loads. Solving the structural problem, we have the final result. With the numerical and mathematical procedures defined, the implementation is made using the Python programming language. OpenPulse is an open source software written in Python with the requirement of installing the libraries NumPy, SciPy, VTK, PyKT, and Matplotlib. A friendly interface allows the user to import the geometry of the pipe systems, lines in IGES format, insert materials properties, set sections, and import pressure, acceleration, force loads from measurements or theory. After defining the finite element mesh for the model, the user can plot the pipe and system geometry, see the finite element mesh, and run the desired simulations after a proper setup. It is possible to plot the formed shapes, frequency plots of acoustical and structural responses, stress fields, and local stresses or desired sections. Today, we are sharing the content of our repository in the GitHub website in this address, where you can download the codes, examples, theory references, etc. The OpenPulse is under development, and the idea is to allow all users to participate with us in the development and on the validation of the software. And now, a simplified example of application. This is the OpenPulse main window. You can load a geometry file and specify the length of your element. The tiles of the mesh can be thin. You can set properties for different parts of the structures, and you can set different sections. For a structural part, you can apply displacements, boundary conditions, constant or from tables. You can set springs, mass, dampers, forces. And for acoustic part, you can set pressure, constant or from experiments, impedance, corrections, etc. Now we are performing an harmonic analysis, and we can see the result for the coupled problem. Displacements, spectrum, frequency plot of displacements or reaction forces. We can see stress, different kind of stresses, stress spectrum, pressure field, and frequency plot for some pressures. And now, to conclude our presentation, we can say that a numerical procedure to model low-frequency acoustically induced vibration caused by compressor pulsation in gas pipeline systems is under development. The obtained procedure is being adapted to an open-source software, the OpenPulse, which is now shared with the interested public to test and validate. More features like valves, chambers, supports, flanges, etc. are being developed and are not presented here. A validation phase is being planned to next year, with experimental tests in a refinery plant. We acknowledge the support from Petrobras, Universidade Federal de Santa Catarina, and Agência Nacional de Petróleo, Gás Natural e Biocombustíveis. Thank you for your attention.